Then coming to the problem now. So here we are taking a two-span continuous beam. So here you can see that this is a ABC span, and whereas in AB you're having a 80 kilonewton meter, so which is of 6 meters length, and it is a equidistant at the center, that is 3 meters. And whereas for BC span you're having a UDL of 10 kilonewton per meter, and it is of 5 meters distance. So here you are going to have EI is constant throughout. So you are going to analyze this two-span continuous beam by using a slope deflection method. And then you're going to draw the elastic curve, bending moment diagram, and shear force diagram. Now coming to your step 1, you're going to determine the degree of freedom. So for this, you can just see, so this is a support. So here in this support, it is a fixed support. Therefore, the rotation and translation will be 0. So that means theta and delta at the A point will be equal to 0. Whereas coming to the B node, you are having, it is a roller support. There you are having rotation, but you are not having any translation. That means theta B not equal to 0 and delta B equal to 0. Whereas coming to C point, you are having both rotations and translations are to be equal to 0. So now the degree of freedom for this problem is 1. So that means it is theta B. Now coming to your next step, you are going to calculate the fixed end moments. So how you are going to calculate your fixed end moments? So for this beam, we are going to assume all the supports to be a fixed supports. So here A, B and C are assumed to be fixed supports. And here you are going to take AB separately and BC separately. So here you can see that this is AB beam. So for this AB beam, we are considering both ends to be fixed ends. And here the point load of 80 kilonewton. And when we apply a 80 kilonewton meter, so here you are going to have fixed end moments to be in hogging direction. So this is hogging direction at A and B. So at A, since it is in anti-clockwise direction, as per sign convention, it is negative. And the formula for point load at the center for the fixed end moments is WL by A. Similarly, for B, it is a clockwise direction. Therefore, it is positive. Here you are having plus WL by A. And then calculating the fixed end moments for AB and BA span. So this is negative and this is positive. So it is minus 60 and it is plus 60. Now coming to the next span, that is your BC span. So here you are having a UDL of 10 kilonewton per meter. So here you are getting same hogging moments at B and C. So at B you are having anti-clockwise. So therefore it is negative. And the formula for this is WL square by 12 when you are having a UDL. Similarly at C it is a clockwise direction. Therefore it is positive. And here you are having plus WL square by 12. And finding out the fixed end moments at BC and CB, you're having minus 20.83 and plus 20.8. So this is how you're going to calculate the fixed end moments. Now coming to your next step, that is slope deflection equations. So coming to this slope deflection equation, so these are the generalized equations for MAB and MBA. So MFAB is nothing but fixed end moments due to the external load. And this 2I by L into 2 theta A plus theta B is nothing but your fixed end moments that is developed due to rotation. And this minus 6I delta by L square is the fixed end moment that is developed due to the settlement. So together we are having the complete equation. So in this problem, we are not having any settlement. Therefore, delta will be equal to 0. So next, now what the slope deflection equation will become? So this part will be equal to 0 and this part also will be equal to 0. Now the MAB will be equal to MFAB plus 2I by L into 2 theta A plus theta B. Similarly, MBA will be equal to MFBA plus 2I by L into 2 theta B plus theta A. So these are the slope deflection equations we are going to use in this problem. Next, you're going to substitute these slope deflection equations for both the spans. So here, if you just consider the beam, so this is a beam, right? So here, this is A support, This is B support and this is C support. So here theta A will be equal to 0. Why? Because it is a fixed support. And here theta C will be equal to 0. So now we are going to substitute these two things in the slope deflection equations. So MAB, so here I have written, since it is a fixed support, theta A will be equal to 0. So while substituting this, that means here theta A will be equal to 0. So now your MAB equation will become like this, minus 60 plus 2EI by 6 into theta. So that means it is minus 60 plus EI into theta B by 3. Similarly, MBA also will be equal to 60 plus 2EI by theta B by 3. So this will become 0. Next, similarly for the slope deflection equations, so for the span BC, MBC will be equal to MFBC plus 2EI by L into 2 theta B plus theta C. So here you are having theta C will be equal to 0. So that means MBC now will become minus 20.83 plus 2EI by 5 into 2 theta B plus 0. So now similar way, MCB will be equal to MFCB plus 2EI by L into 2 theta C plus theta B. So now MCB also will become, so here theta C is equal to 0, right? So this will become 20.83 plus 2EI by 5 into theta B. So this is for BC span. Now when we use the equilibrium equations in your step 4, what will become? So here sigma MB will be equal to 0. So that means it is a joint equilibrium condition. So for suppose if you just consider this ABC beam, two span continuous beam. So here B will be your joint. So that means sigma MB will be equal to 0. So that means MBA plus MBC will be equal to 0. Okay. So now by substituting this entire thing and solving this equation, you are going to get theta B will be equal to minus 26.7 by EI. So that means where you are getting negative means as per sign convention, it is an anti-clockwise rotation. Now we are going to draw the elastic curve. So here I am going to draw the continuous beam ABC. So this is your two span continuous beam. So this is your A. This is your B and this is your C. So now here we know that theta A equal to 0 and theta C equal to 0. Coming to your theta B, so it is 26.7 by EI. So which is in anti-clockwise direction. So this is anti-clockwise direction. So now here theta A is 0 and this will become like this. And again the curve will move up and again it is in the, again here coming to theta C, it is becoming 0. Now when we draw a tangent to this, so you can just see. So here we are applying the anti-clockwise rotation we are getting. So that is the representation of your elastic curve. So here we can have a note that, so if you are getting negative, so that means it is a anti-clockwise direction. So now you are getting a clockwise means, so it is a positive value. So anti-clockwise rotation means it is negative value. Okay. Rotation. So this is how you are going to draw the elastic curve. Now coming to your next one. So that is calculation of your final end moments. So as you got theta B as 26.7 by EI, which is in negative direction. So that one you are going to substitute in this MAB. You are going to get MAB as minus 68.9 kilonewton meter. Similarly MBA, similarly MBC and MCB. So here we are using theta B is equal to minus 26.7 by EI. So finally we got the final end moments. Now, so you are going to draw the bending moment diagram. So this is your MAB minus 68.9 kilonewton meter, MBA 42.2 kilonewton meter, MBC minus 42.2 kilonewton meter, MCB that is 10.15 kilonewton meter. So now I am going to draw the free body diagram first. So this is your AB and this is your BC span. And for your AB, you're having a point load of 80 kilonewton. And this is 3 meters and this is 3 meters. Total 6 meters you're having. And next is your UDL of 10 kilonewton per meter. So here you are having a 5 meters. So now I am applying this moments, okay, final and moment. So 68.9 is in anti-clockwise direction. Why? Because it is negative. So it is 68.9 kilonewton meter. And again, MBA, it is positive, therefore clockwise. MBC again negative, so it is anti-clockwise. So that is 42.2 kilonewton meter. Again, MCB, it is in positive, so it is a clockwise of 10.15 kilonewton meter. Now, the reactions that are going to develop at A is RA. At B, it will be RB1. Why? Because it has been divided with BC span also. So here it is RB2. And now at C, it is becoming RC. So this is the free body diagram. Okay. So based upon this, you are going to draw the bending moment diagram. So coming to your bending moment diagram, so I am drawing A, B and C. So coming to this AB span, so first we will take the external load and the reaction part only. So that means it is looking like a simply supported beam. So for simply supported beam, so you are going to have the sagging moment. So that means it is a positive. So this is your sagging moment. Okay. So for this sagging moment, so as it is a point load at the center, so we are having a triangular of WL by 4. So which is of 80 into 6 by 4. So that will be equal to 120 kilonewton meter. So which is of positive. Now coming to your BC, so that is UDL. Therefore, it is a parabola of, sorry. So it is a parabola of 31.2. So this is 30, So this is WL square by 8. So that means 10 into 5 square by 8. So that will become 31.25 kilonewton meter. So this is also again a positive. So this is a free bending moment diagram. Now coming to this final end moments. So that will be in hogging nature. So that means it is negative. So this is a hogging moment. So these are the sign conventions actually. So sign convention. So sign conventions for bending moment diagram. So now here it is a 68.45, 68.9. So this is 68.9 and this is 42.2. So this is 42.2. So this is 68.9 kilonewton meter and this is 42.2 kilonewton meter and this is 10.15 kilonewton meter. So you just join these lines. Okay. So this is negative, and this is also negative. So now our final bending moment diagram will be the shaded portion. This is your final bending moment diagram. So it is an intersection portion of your free bending moment diagram and fixed bending moment diagram. So this is bending moment diagram. Okay. So now I think you understood. Now coming to the next one, it is a shear force diagram. So to draw the shear force diagram, again you have to find out the reactions. So first we will draw this A, B and C. So this is again a point load of 80 kilonewton and this is a UDL of 10 kilonewton per meter, and this is 3 meters, 3 meters, and this is 6 meters per AB, and this is 5 meters. So coming to this, so this is 68.9 kilonewton meter, and this is 42.2 kilonewton meter, and this is 10.15 kilonewton meter. So now coming to the reaction, so this is RA, and this is RB1, and this is RB2, and this is RC. So now coming to this, so sigma MB if you have taken, so the moment at this point is fogging in nature. So that is minus 42.2 kilonewton meter. So now what we are going to take, RA into 6, okay, minus 68.9 minus 80 into 3 will be equal to minus 42.2 kilonewton meter. So from this you are going to calculate RA. Okay. Similar way, so here you are going to get RA to be 44.45. Similar way, now RA plus RB1 should be equal to 80 kilonewton. So that means your RB1 will be equal to 35.55 kilonewton. So this is your RB1. Now similar way, when we take sigma MC, that is equal to minus 10.15 kilonewton meter. So that means we are taking moment about this point. So that will become RB2 into 5 minus 10 into 5 into 5 by 2. So that is UDL. Okay. Minus 42.2 will be equal to minus 10.15 kilonewton meter. So here RB2 you are getting it as 31.41 kilonewton. Now RB2 plus RC will be equal to 10 into 5. So this implies RC will be equal to 18.59 kilonewton. So this is your RC and this is your RB2. So after getting these values, how to plot the shear force diagram? So shear force diagram means, so just if you take a segment of a beam, right? So the shear force will be represented like this. So when we cut a section at this point, okay, so this will be section. So when towards left, if you are having upward arrow, so that means clockwise shear. Similarly, towards your right, if you are having downward arrow, so that means again it is in clockwise shear only. So that means it is a positive shear. So same way, if you take a small segment of dx, and this is downward towards left and this is upwards towards right of your section. So this is left of your section and this is right of your section. So now it is in anti-clockwise direction. So that means it is negative shear. So by using this sign convention, I am going to draw the shear force diagram here. You just see. So this is your A, this is your B, and this is your C. So for this, if you just draw a section here, so this is in clockwise direction, RA. But RB1 is in anti-clockwise direction. So that means, so this is your RA. Okay, so again, till here it is same. Again, down you are having a 35.5. So that means it is 44.45 kilonewton. And this is 35.55 kilonewton. So this is plus and this is negative. Whereas coming to RB2, again it is 31.14 and RC2 is 18.59. So it is linearly varying. Why? Because it is of UDL. So this is plus and this is minus. So this is 31.41 kilonewton and this is 18.59 kilonewton. So this is your shear force diagram. So you have to shade this like this. Okay. So here moment won't come into picture while calculating the shear force. So here for any continuous beam, the shear force diagram will looks like a shear force diagram of a simply supported beam only. If you just make it in a two different spans, I mean, if you draw it in individually like this, so this will become a shear force diagram. Clear? So these are the references from where the problems have been taken. Thank you.